Question 6 is the continuation of trigonometry. As you would know that it is broken down into different parts, so it's quite large and it takes a lot of marks. Now under 6.1 they say here that the quotient identity tan x minus y is the same as sin x minus y over cos x minus y. Now remember that a quotient identity is an identity that tan of theta is equals to the sine of theta over the cos of theta. So this really is the same thing. That's what they mean here. The unique thing that happens here is that we have compound angles here, meaning we have two angles that have been subtracted instead of a single angle, but we still see the same identity here. That's what we are given there. Now under 6.1 they say here use the compound angle identity to derive a formula for this tan x minus y in terms of x and y. So what we're going to do here, we're going to use a compound angle identity. We are being instructed, they tell us where we should start and what we should do. And the idea is that we have to simplify this so that it's only written in terms of tan x and tan y, because here you can see it's written in terms of cosine and sine. So we need to change that. Now what I'm going to do then now with this question, we are going to start on a new page here looking at question 6. We are looking at 6.1. We have here the tan of x minus 1, which really has been changed to a quotient identity as we discussed. And under 6.1.1 they then say we should use the compound angle identity. Now remember, we don't have a compound angle identity at grade 12 or at high school level for tan. So that's why we're going to use here, we're going to start at this stage here. It means I'm going to say here the right hand side is given by the sine of x minus y over the cos of x minus y. Therefore we are going to expand these two using that compound angle identity. With the sine, we know that it's going to be a sine of x cos of y minus the cos of x the sine of y. Now this formula is there in the information sheet. If you don't know it, simply just go there and take it. But I can give you a tip in terms of how you can remember it. When we deal with sine, the trig ratio sine is a synonym, or it sounds like the word sine as in positive or negative. Now if you are dealing with sine, the sign does not change here. The sign remains the same when you expand, but your ratios, they change. We start with a sine, we get a cos, sine of x and sine of cos. Then we swap them around. We start with a cos, then we have a sine. I hope that helps. Now we're going to then expand the cos. So with the cos, I'm going to have a cos of x, cos of y, plus the sine now of x and the sine of y. Again, you can get this in the information sheet, but again I can give you a tip in terms of how to remember this. We can say this is cocoa melon. So this means that when we are dealing with a cos, when we have a cos, then we're going to have the same trigonometric ratios, cos, but obviously it will take the different angles. Then because already I have a cos, it then means the ones that are coming after the cos would be the sine, and of course they'll take the different angles. However, you must note that when we have the cos, when we're dealing with the cos, the side will change. If this was positive, it will then become negative. And that is simple as that to really remember. Now we are going to move forward. The next step that we're going to do here, I need you to really pay attention because it's a tricky step. I'm going to rationalize this equation or this expression. The reason why I'm rationalizing is that I am stuck. There's nothing much that I can do here. I can't take out the common factor. I can't combine these things. They really have different angles. Now, rationalization is a method that I call do something but nothing. What I mean by that is that we are going to use this denominator here, cos x and sine y, as a ratio that we're going to rationalize with. The reason being is because I can see that when I divide by that ratio throughout, the tangent will come back. So let me show you what I mean. I'm going to then say here, I'm having a 1 over the cos of x times the cos of y. I'm taking this, putting it in the denominator and putting a 1 here. And I also divide here by the same number, the cos of x, cos of y. Then here I still have my original expression. Now let us go through this and see what I've made here. Well, what I've done here is that I've done something but nothing, because these two can simply cancel each other. Then I'm left with this part as it was. So really I haven't done anything. I just divided here by 1, or I've multiplied this whole thing by 1, because this is a 1 really. And here I've kept everything the way it is, you know. This is still that and that there. Now from here we then go into multiply this with each term inside the brackets there, so that now I'm going to have the sine of x cos of y all over cos of x cos of y. This is this first part here. The second part will be that where I'm going to have a minus cos of x sine of y all over cos of x cos of y. Remember, the 1 multiplies this number, so it sits here, and this one will multiply an invisible 1 there and here, you know, that's why it will sit there. Now I still have a division line here where I'm going to do the same expansion that I did here, distributively. I'm going to multiply this and that together, so that I have here the cos of x cos of y all over the cos of x cos of y. Then I'm having a plus here, the sine of x, the sine of y all over the cos of x, the cos of y. Now let us look at what is happening here. You would see that my reason of saying why I rationalize is coming to life now, because I said that when we rationalize with this denominator here, we actually bring back the tangent, you know, because I'm having now these ratios dividing each other. The tangent will come through, because you must notice that some of these three ratios will disappear, you know, the cos and the cos here would cancel each other. The cos and the cos here will cancel each other. And this whole thing here cancel each other. So I'm having a 1 here because they're exactly the same. The last one, there's really nothing that cancels. You know, here they're different. They don't really cancel with each other. Now, this would be much more simplified now. It can be something that is much more simplified. Why? Because when you look at the remaining ratio here, it can actually be written as an identity of a tangent of x. That's how the tangent comes back now. Because remember, our question was that we should write them in terms of tangent of x and y. So that's why I actually rationalized. Now here I'm going to have a negative. Again, if you look at this, it brings back the tangent. So it's going to have here, we're going to have here the tangent, not the sine, but the tangent of y. And we are dividing here by a 1, because this whole thing cancelled and we have a 1 there. Then we have a plus. Now if you look at this, the sine of x and cos of y, they give me a tangent again. So this becomes a tangent of x, and the sine of y and the cos of y, they give me a tangent of y there. And at this stage, there's nothing really we can do because everything is in terms of tan x and tan y as the question requested. And we are done. So this gives us a total of 4 marks. Where we are going to get our first mark for doing the expansion, applying the compound angle identity. And we're going to get a mark again for rationalizing, both at the top and the bottom, numerator and denominator. And we're going to get a mark here for simplification, simplifying things there and cancelling things, working things out there. And we get the last mark really for the final answer, which really includes as well going back to our identities of tan. And that should be a total of 4 marks for 4 minutes. Now, the next question that we are going to look at is question 6.1.2. 6.1.2, it says here that hence or otherwise show that this tan 45 plus 60 degrees is indeed equals to negative 2 plus negative 2 root 3. Now with this question, we are having here tan 45 plus 60 degrees, and we have to show that this is equals to negative 2 plus root 3. Now, when we say hence or otherwise, it means that we need to use what we have deduced from the previous question in this new question. Otherwise would mean you can use other methods. And I always advise that don't use other methods because usually they'll be long and lengthy. But if you use what you already have done in the previous question, it becomes easy because it's a continuation. So here I'm going to really take the left-hand side, which is given by the tan of 45 plus 60 degrees. And, what I'm going to do here is that you have to notice that this is the same as tan x and y, it's the same as tan x and y. Except now the x is 45 and the y is 60. And we just proved here that if you have such a trigonometric ratio, it can actually be written as tan x minus tan y all over 1 plus tan x times tan y. So it's like I'm using this as an identity. So what I'm going to do now here, I'm going to say we are going to start with the tan of the first angle here. So we're going to have tan of 45 degrees, and then we're going to subtract tan of the second angle here, y. Remember, I'm saying that here we are having tan of x minus y. So this would be a minus tan of 60, which is what we said it's the part that speaks to y. And we are dividing here by 1. So we're going to have a 1. Then we are adding the product of these two. So the 45 and the y. So we're going to have plus the tan of 45 times the tan of 60 degrees. Then we can simplify this. When you look at these trigonometric ratios, they're actually made up of special angles. And we all know that the tan of 45 is a 1 minus here the tan of 60 is really root 3. We're having 1 plus the tan of 45 is a 1, and the tan of 60 we're saying is a root 3. I'm just writing all this as special angles. Now when you look at this, remember we have to come to this final answer there. Now when I look at this, it means I'm going to rationalize again, because I want to remove this bottom part here. So it means I have to do something but nothing. Now the way to do that for this one is that I'm going to say 1 minus root 3 all over 1 plus root 3. Then I'm going to multiply here by 1 minus root 3 over 1 minus root 3. So I'm taking the numerator now, then I'm multiplying by that numerator as a ratio here. Remember, this and this would cancel each other out, and I'm having a 1. Then if you say 1 multiplied by this whole thing, I get the whole thing here. So I've actually haven't done anything. I've done nothing here, but I've done something, you know, if you get what I mean. Now, the reason why I chose the numerator to multiply by the numerator here is because I want to remove the denominator. You see here, we don't have a denominator anymore. You know, it's like we have a 1 there. We don't have anything at the bottom. So now at this stage, we'll then continue. If you look at this, we're going to multiply this 2 here. This is the same as saying I'm having a 1, 3 squared. It's you know, it's 2 of this. So to expand this, we are going to say 1 squared, which is just a 1. Then we're going to say 2. We are going to say 2 times 1 times root 3. So it's 2 times 1 times negative root 3. And this gives me negative 2 root 3 there in the middle. And then the last part is that we're going to square the negative root 3. You know, the way you expand binomials. So this is going to be plus a 3. So I'm saying here we're having x minus y, and you square that. This is the same as x squared, because you square the x first. We take the 2, we multiply it with the x and the y. That becomes 2xy. Then we square the y. That's what I'm doing here. Then here at the bottom, you would see that we have a difference of 2 squares. Right? This is the same as having x minus y and y plus x plus y. This would simply be x squared minus y squared. So I'm basically just squaring x and y here, and I'm putting a negative there. Now that's what I'm going to do here. If you square the 1, it's going to be a 1. If we square the 1 here, it's going to be a 1. Then if we square the 3, it's going to be 3 here. And then remember, we keep the negative here for difference of 2 squares. From here, we then can simplify so that we now have 1 plus 3 to give me a 4 minus 2 root 3. And here I'm having 1 minus 3, which is negative 2. And I can divide each term by that negative 2. I can say here I'm having a 4 divided by negative 2. I'm having here 2 root 3 divided by negative 2. And you can see that here I'm going to have a negative 2. And here the negative and the negative will give me a positive. However, the 2 and the 2 would cancel each other out, so that I'm having now the root 3. And hence, this is proved. Hence, this is shown. We really have shown that this is equal to that. And this carries 3 marks. So we're going to get our first mark from firstly using our identity, you know, moving from here to there, because we notice that we have to use the identity we have derived from the previous question. And the second mark will really come from applying the special angles, you know, writing the special angle for each trig ratio there. And the other mark will be the final mark, really. The next question, which is question 6.1.3. 6.1.3, they say here, for which values of x and y is tan x minus y not valid? Where is this function? Where is this trig ratio not defined? Now, you know, the best way to think of this is that you must remember that we have here tan x minus y, and we said this tan x minus y is really the same as tan x minus tan y all over 1 plus tan x times tan y. So where is this thing not defined? Well, traditionally, you must think of, the best way to answer this question is that you must think of a function f of x is equals to tan theta. This function, we all know that, it will look like something like that. Here, at 90 degrees, there's an asymptote. And this function would really move like this. It will move as close as possible to the asymptote, but will never touch the asymptote. That implies that the function here is undefined. If you were to put a theta of 90 here, the function is undefined. You will get error in your calculator if, let's say, you put it on the calculator. We're going to use the same logic here when we look at this, because this is still a tan, even though here we have compound angles, meaning angles that subtract each other. Let us use this understanding of the graph to the question that we have. If we consider the tan x minus y, so I'm going to say here for tan x minus y, we will say here that x minus y should never be equal to 90 degrees. So I'm saying here that this thing here, the compound angles here, when we combine them, they should never give us 90. They can give you any number other than 90. Because if they give us 90, this whole thing will be undefined. It's why we have the asymptote. The function is not defined at that point. However, it is important to note that we also include angles that are negative and angles that are bigger than 360 degrees. That's why I'm writing this as a general solution or a general restriction or limitation to this, to say not only 90, but also angles that will be bigger than 360 degrees and those that will be negative. How do I mean? If we put here a 0, this whole thing will be a 0. We get the angle of 90. This is this point here. However, if I put a 1 here, I'm going to have 1 times 180 degrees. It gives me 180. Then we say 180 plus 90. And this will give me a 270. It means somewhere here we'll have 270 degrees will be another asymptote, and the graph will be going like that there. So the graph also will not be defined. And if we put a negative here, we come into this side, we'll have a negative number this side, like a negative 90 here. The graph also will have an asymptote on the other side. So this includes all the numbers that will be bigger than 360 and the ones that are negative. So this means this thing will continue like that from positive infinity to negative infinity. There will always be asymptotes as we go to positive infinity and negative infinity, where this function or this trig ratio that we are given is not defined. So those will be all the values that are there. However, we have to also note that this trig ratio that we're dealing with now is the same as that. We have proved that it is the same as this trig ratio here. And this consists of tan x, tan y. Therefore, this means we also have to consider them. We're going to apply the same conditions really for them to say that if, for example, you focus on the tan of x, the x should never be equal to 90 degrees plus k 180 degrees, where k is an element of integers. The same is really true for tan of y. X should never be equals to 90 degrees, but not only 90, but including also the positive and the negative, and also angles that are bigger than 360 degrees. Now, this is only 3 marks, and you should get the 3 marks really from all these 3 different conditions that are there. Moving along to the next question, we are told here in question 6.2 to prove this identity here. So we have here 6.2, we are given the tan of a all over 1 plus tan squared of a to be equals to the sine of 2a. Now, a tip that you have to always take when you're dealing with proving identities is that take the side that is the most complicated, because it's the one that needs to be simplified. And when we look at these two sides, we can see that this one is more complicated than this one. So it means I'm going to focus on the left hand side, so that now on the left hand side I will start by changing this to its identity, so that it is a sine of A divided by the cos of A, and this will be all over 1 plus the sine squared A all over the cos squared A. I'm just using here a quotient identity, changing the tan here to be sine over cos. Now from here we are then going to simplify a little bit in our denominator. I'm going to keep this as it is for now, and say that here I'm going to take an LCM cos squared A. I'm going to take an LCM. This is over 1 here. So perhaps let me write this down here. Then I'm going to now say 1 into cos squared A. It goes cos squared A. Then I'm going to say cos squared A times the 1 in the numerator. I should get here the cos squared A. Then I'm going to say the cos squared A divided by the cos squared. It goes once. I'm going to take the 1 and multiply it by the sine squared A. So here I'm going to have a plus sine squared A. Now as we move along, you'll come to realize that at the top we still have the same thing for now, because there's nothing much I can really do there. But when you look at this, it transforms to the identity of 1 here, because I'm having a cos squared and a sine squared. So I'm going to have a 1 divided by the cos squared A. Now at this stage I'm simply going to say the sine of A over the cos of A. Then I'm going to multiply. You know, here these things, they are dividing each other. When we multiply, we change, we reciprocate the denominator and the numerator. I'm going to take this, take it to be the numerator, and take this to be the denominator, so that I'm having a cos squared A divided by 1 now. And what is going to transpire here is that the cos would cancel here. I'm going to have 1, but here I'm going to be left with only 1 of it, because remember, here I'm having 2 of them. I'm having cos A times cos A here. 1 of them would cancel and I'm left with only 1. Now, the next step following this really is to then multiply this 2, this times that. It's going to give me a sine A cos of A, and we know that this is a double angle identity for sine, which is going to be the sine of 2A. And this is really equal to the right hand side. Hence proved. And this question really carried 4 marks, where the first mark will come from changing these identities, changing the identity of this to a 1. The other mark will be simplification and really finding or proving that the 2 sides are the same. Going to the next question, we are given an expression here cos of negative theta, sine of 180 degrees plus theta divided by the tan of theta minus 180, the sine of theta plus 90 degrees. Now the first thing that I'm going to do really here is that I'm going to fix these angles here so that they sit properly the way I can relate to them in my mind. So I'm going to just keep this as they are for now, the numerator, and really start writing this as I'm going to take out the common factor here, so that it sits as a reduction formula that I can relate to. So here it means I'm going to have 180 degrees minus theta. So this means if I multiply this by that, I get a negative 180. if I multiply this by that, I get a positive theta. So I just took out the common factor there. Now, for this one, I'm going to have a sine of, I'm going to just take the 90, put it in front here, and I'm going to have that. Now, let's do the work. We know that the cos of negative theta is just cos of theta. And we can see that this is the third quadrant. And in the third quadrant, sine is negative. So that means I'm going to have a negative sine of theta. And when we look at this one here, we are firstly going to consider the negative here. We know that the tan of a negative is negative, the tan of that angle. So here I'm going to be left with 180 degrees minus theta. And we also know that this is the second quadrant, and sine is positive in the second quadrant, but it changes to its cofunction. That means it's going to be a cos of theta now, but it's going to be positive because it is in the second quadrant and sine is positive there. You must remember your X diagram, or the cast diagram as some people will normally call it. Now from here, we will then continue to say here that we have a negative cos of theta, sine of theta. I'm just multiplying these two, and I can then change the tan, because we can see that here I'm in actually the second quadrant, and the second quadrant tan is negative. So that means here I'm going to have a negative and a negative tan theta. So this negative here is this one, but when we change this, because it is in the second quadrant, it's going to be a negative of theta, and we still have the cos of theta. Now here I can really see that my cos and cos, they cancel each other out, so that I'm left with negative sine theta divided by, I'm going to then change this to a sine theta cos of theta. And really this is the same as having negative sine theta divided by sine theta over cos theta, just to write it a different way so that you know it can be appealing to some of you guys. Now from here, I'm going to do the reciprocal again, where I'm going to have a cos and a sine here, and these two would really cancel each other out, and I'm only left now with a negative cos of theta, and that should be my final answer. Now this one takes on 5 marks. I mean, there's a lot of things that we applied here. The first mark will come from dealing with that reduction formula there, and also dealing with the reduction formula for tangent, and also for cos. You know, we also did this one here. You'll get a mark for that. And the other one would come when we change this tan to a cos, and really you'll get the other one to be there. The final mark will be there. The last question here is 6.4, which says determine the general solution for this equation here. Now our equation is given as cos theta is equals to the root of sine 2 theta minus sine squared theta. Now the first thing that I'm going to do here really is to square both sides. I'm going to square both sides to remove this square root. So this side I'm going to be left with sine 2 theta minus sine squared theta, and this side I'm going to have a cos squared theta, because you know when we square this, it's going to give you a cos squared theta. And I see something interesting after doing that. this sine and this cos, I see a 1 there. If I take the sine to this side, because I'm going to then have the sine squared theta is going to be positive plus the cos squared theta. Remember, I'm taking this to this side, it becomes positive, and this has always been positive. Now I'm only left this side with the sine 2 theta, but this becomes 1, and here I'm having 2 cos theta. Now when it's like this, I can then apply my general solution, where I'm going to then say 2 theta is equals to the sine inverse of 1 plus k 360 degrees, or the other general solution that we have for sine, it will be 2 theta is equals to 180 degrees minus the sine inverse of 1 plus k 360 degrees. And we are saying that k here has to be an element of integers. Now if you then pull a calculator and we do the sine inverse of 1, it gives me 90. So I'm going to have here 2 theta is equals to 90 degrees plus k 360 degrees, or we're going to have 2 theta is equals to, here we're having 180 minus the sine inverse of 1. That gives me 90 as well. So I'm having a 90 degrees plus k 360 degrees. Now it means now here we are going to divide both sides by a 2 here, so that I'm only left with a theta. So I'm going to have a theta is equals to a 45 degrees plus k 360 degrees here. And I'm not going to do this really, because the same thing is a type of a solution where this happens twice. We have the same number twice, where k is an element of integers. So that is my general solution. It really occurs twice. Now this question is only for 4 marks. We are going to get the first mark for squaring both sides, for using the identity for 1, applying our general solution on both sides, and writing the final answer there.